All right, welcome everyone to today's video. We're going to be talking about digital tooling cooling channels. So a little bit of the work that we've done with water cooling our mold tools to improve cycle times. So I'm Ben McDonald, application engineer at Fortify, and I'll be taking you through what we did and what we found. To start, we're going to talk about why printed tooling. So it's really simple. You're saving time and money when you're using printed mold tools in order to mold small volumes of parts. So you're able to get a tool in 3 to 6 days as opposed to 3 to 6 weeks for a fraction of the cost of that steel mold tool. It really enables quick turn prototyping and functional end use materials. You're able to do complex designs with these tools, and it's really speeding up your prototyping cycle. We do this with our digital tooling resin. It's the best resin on the market for printed mold tools. It's a ceramic fiber reinforced material, has a very high HDT of greater than 300 C. It's fully isotropic, or the parts printed are fully isotropic, and it has a best-in-class resolution and surface finish. So it's really a great material to do this prototype molding with. But today, one of the kind of not talked about secrets of these printed mold tools are the cooling times and the cycle times that result from these cooling times. So today, when you're running one of these mold tools, you're looking at a cycle time of roughly 2 to 3 minutes, which for a handful of parts, 50, 100, 200 pieces, it's not that big of a deal, but it does add up very quickly. So while you're able to get a mold tool very fast, molding can end up being very slow depending on how quickly you're able to cool your part. So today we're doing this with just a fixed air nozzle that we have mounted on the mold press, and we're blowing compressed air on the surface of the tool. So our cooling process is really a two-stage process where we do just the initial cooling with the tool clamped. So this is anywhere from 50 to 100 seconds with the tool clamped in order to solidify our part. We're just looking to get our part out of that molten phase into a solid phase so that we're able to do the bulk of our cooling with this compressed air. The compressed air ends up taking anywhere from 15 to 30 seconds depending on the part size and the temperature of the plastic that we're injecting into the tool. So in total, we're looking at anywhere from 70 to potentially 120 seconds of cooling time that really drives up our cycle times, because I mean, that can be upwards of 2 minutes alone just for cooling the part itself. So that's really what our problem is today. So the problem is we have long cycle times, which compared to a metal tool, we're looking at 3 minutes versus 45 seconds, which that's really a limiting step. So like I said earlier, it's great for molding a few hundred pieces, but if you're looking to get up to 1,000 pieces, you're looking at multiple days of molding in order to achieve this. With our material, the real limiting factor is cooling, but that's due to the thermal conductivity. So our thermal conductivity is on the order of 0.6 watts per meter Kelvin, which is an order of magnitude lower than steel and 2 orders of magnitude lower than aluminum. So looking at that value, we're really not in a good starting position to actively cool our tools. It's still possible. We're still able to transfer heat from our tool into water, but it's just going to be at a slower rate. Metal molds, they're getting to these 45-second cycle times, mainly with this water cooling. So they'll do very complex channels, like we can see in some of the images here, where they're either using drilled holes or in some instances, they're doing conformal cooling, which allows them to get very close to the part with their cooling channels so that they can maximize the cooling efficiency of a mold tool. We have the power of additive. So that enables a lot of design freedom where we can go ahead and optimize cooling channels, whatever we want to do there, we have that freedom. So the real question for today is, can Fortify mold tools realize similar benefits from active water cooling? And we're going to look at that a little closer here. So we started out with our mold tool pictured on the right. Using Creo, we were able to generate a lattice cooling channel, which that's really a key detail of this whole cooling setup. The lattice cooling channel, it enables structural support due to the nature of a lattice geometry. What it also enables is a lot of surface area inside of that cooling channel. If we look at our heat transfer equations, we can easily see that with a constant thermal conductivity, we have two real parameters we can pull on. That's the distance from the mold surface to the cooling channel, and then the surface area of the cooling channel itself. Optimizing for both of those parameters enables us to really maximize the cooling benefits that we might be able to see. So using that knowledge, we designed this lattice geometry, knowing that we're going to be able to maximize the surface area of our cooling channel, so we have more water coverage that's pulling heat directly out of that mold block. We're also able to reduce that wall thickness between the surface of the mold and the cooling channel. So we ended up using 5mm wall thickness from the surface of the mold tool to the cooling channel. That's very important because minimizing that distance enables us to pull more and more heat directly from the surface of the tool. So, and on top of that, we still had our structural rigidity with the lattice geometry. So we knew that our mold tool, so we knew that with our mold tool, we were able to minimize that distance and still maintain structural rigidity during that molding process. With that design, we went to our printer, our Flex 1 printer, and we were able to print this full tool. So mold set plus inserts for the targeted insert areas. As a side note, this is a very cool tool. This is a sales piece that we are actually using different textures to show off Fortify capabilities, as well as a material insert, so calling out what material we're molding parts with. This tool, we printed this full mold set 6 hours. In 2 days, we were able to get this tool on a press. So we're talking about starting a print on day 1, cleaning, post-curing at the end of day 1. On day 2, we're molding parts. So that's very fast. That's really realizing the value of additive tooling. With this tool set, we ended up running 200 shots of polypropylene. So we were really looking to see how fast can we mold 200 pieces of polypropylene with this tool and with a control tool with no lattice geometry, so that we have a good comparison to make here. During this mold trial, we ended up using 10 tons of clamp force, and that was just enough so that we were able to minimize, or I should say eliminate, flash on the parting line surface of the tool itself. We used 2200 psi for our injection pressure, 25 millimeters per second for injection speed, 1500 psi for our pack pressure. So pretty standard parameters for us when we're molding polypropylene, especially for a fairly flat geometry like this part. But this was a very good candidate for our cooling because it has a large surface area on the part itself. So there's going to be a lot of heat distributed throughout the full tool. The results. This is really the key thing that we found here. So running these two tools, water cooling versus control, we saw about a 50% reduction in time to mold 200 pieces. And that's something that's super important for a real world use case. So if we look at any one of our partner CMs or ourselves internally, if we have to mold 200 parts, which is a pretty standard quantity of parts to mold for us, we're able to do 2 different geometries molded in a single day because we're able to mold 200 pieces in 4 hours. So if we look at our 8-hour workday, that's 2 mold tools we're able to process in a single day, effectively doubling our capacity to mold parts. On the other side, we're looking at potential cost savings. So if your molding step is only taking 4 hours as opposed to 8 hours, there's definite cost savings there that could be passed off to customers. So it's really a powerful thing that we found here. And this was with a really non-optimized lattice geometry. This is something that we're going to be looking further into to see really how much we can push this process, how fast can we mold our parts, with our goal being getting somewhere close to an aluminum tool. Because if we look at the rest of our molding process, the injection phase, it's very similar to a metal tool. It's really just that cooling phase that adds so much time to our process that we're able to really reduce with this lattice water cooling. So thanks for tuning in, everyone.